And welcome to Geometric Sequences, Part 2. And let's discuss the sum of a finite geometric sequence. So if you remember from arithmetic sequences, we had a formula n over 2 times the sum of the first term and the last term that helped us find the sum of a finite arithmetic sequence. Now we're going to talk about the sum of a finite geometric sequence. So hopefully you're finding a parallel between part 1 of arithmetic sequences and part 1 of geometric, and then part 2 of arithmetic sequences and now part 2 of geometric. So this time, instead of deriving the formula first, I want to give you the formula first, and then on the next page we're going to prove it. So the sum of a finite geometric sequence with n terms is given by the sum sub n is equal to the first term times the numerator 1 minus the common ratio raised to the nth power over 1 minus the common ratio. You are not allowed to cancel in any way because 1 minus r to the n is not the same as 1 minus r. Remember that a sub 1 represents the first term and n is going to represent the upper bound. So why does this work? We're going to come on down to proof, Phil. Yes, if you haven't watched SNL, you don't get it, but it's a Justin Timberlake. Google it. Go on YouTube. But it's getting late and it's getting kind of cheesy around here. So here we go. All right, we're going to start with an arithmetic sequence. A sub 1 is the first term. Then I get the second term, a1 times r, by taking the first term times the common ratio. I get the third term by taking the first term times the common ratio squared, and so on. Now, what if I multiply each of those terms by an additional r? So I'm going to multiply the sequence by r. And now I am going to subtract those sequences. So on the left, I get s sub n minus r times s sub n. Now, see if you can follow this. I have my first term, then I subtract the first term times the common ratio, then I add the first term times the common ratio, then I subtract the first term times the common ratio squared, then I add it again, then I subtract the common ratio times r cubed, then I would subtract that, and so on. So what happens? Well, all of the other terms except for the first term and the last term are going to cancel. So now what I can do on both sides is factor out greatest common factor. So on the left, I factored out an s sub n, and on the right, I factored out the first term. When I divide both sides by 1 minus r, then I yield the formula for the sum of a geometric series the sum of a geometric sequence, or if you have to do a partial sum of the first term times the numerator is 1 minus r to the n over 1 minus r. So let's find the sum, and we'll use a graphing calculator to verify our results. So I have the summation of I equals 1 to 10 of 5 times negative 1/3 to the I minus 1. You need to recognize that this is a geometric sequence because 5 is my first term and negative 1/3 is my common ratio raised to the I minus 1. It follows that form of first term times r to the upper bound minus 1. All right, so if I take s sub n equals the first term times 1 minus r to the n over 1 minus r, my first term is 5. My common difference is negative 1/3. And I raise that to the 10th power because 10 or n represents my upper bound. And you have kind of a royal, what I think, mess of a complex fraction. So if you see on the right, I have put that in my graphing calculator so that it would do the hard numeric computation for me. So the exact value I yield is 73,810 over 19,683, or probably more preferable as a decimal approximation, 3.74. Now, if we want to verify this result on our graphing calculator, okay, then I can go ahead and use the sum feature. So I'm going to press menu. I'm going to add a calculate page. I'm going to go ahead and get the summation. And just to remind ourselves, we started from I equals 1 to 10 of 5 times the quantity negative 1/3 raised to the I minus 1 And notice how it yields the same exact value. And if I hit Control Enter, then I still get 3.74, which would round to 3.75. And welcome to example 6, where we're going to use summation notation to write the sum. So I've given you 15, subtract 3, plus 3, 5, minus some terms that are missing, all the way up to 3 over 625. And we're going to write this in sigma notation. All right, so first thing I need to figure out is the common ratio. So if I take negative 3 over 15, I get negative 1/5. And notice that if I would take 3/5 divided by negative 3, and you see the work there, 3/5 times its reciprocal of 1 over negative 3, I also get negative 1/5. So the common ratio of this geometric sequence is negative 1/5. Next, if I go straight to sigma notation, I'm starting with n equals 1 of a sub 1 r to the n minus 1. What I don't know is my upper bound. I have enough information to fill in the rest. I know that my first term is 15. I know that my common ratio is negative 1 over 5, and that the formula, when we do the nth term of a geometric sequence, we know that we have to raise that to the n minus 1 power. So what I have to do is I have to figure out that upper bound, which you might be able to think that through in your head, but I'm on a video, so I want to show you concretely what's going on. If you think about a sub 1 is 15, a sub 2 is negative 3, a sub 3 is 3/5, then a sub 4, I would take 3/5 times my common ratio of negative 1/5 to get negative 3/25. A sub 5 would then be 3/125 when I multiply that result by negative 1/5. So it would take me to 6 terms in order to get negative 3 over 625. So that means my upper bound would be 6. So I would write this sequence in summation notation as the sum from n equals 1 to 6 of 15 times negative 1/5 raised to the n minus 1. So now let's talk about infinite geometric sequences. Can we find the sum of such a sequence? And if so, what would be a convenient formula? Well, let's take, for instance, the sum of a finite geometric sequence. S sub n equals the first term times 1 minus the common ratio to the n over 1 minus r, but let's make it have the property where your common ratio has to be less than 1, so that's absolute value. So basically a number between 0 and 1, it could be a positive or negative. Well, if you think about this, as n increases without bound, as it approaches infinity, then r becomes arbitrarily close to 0 as n increases without bound. Let's look at a concrete example. Let's look at the base 1/2. 1/2 is a ratio that is where its absolute value is less than 1. But when you take 1/2 to the first power, I get 1/2. When you take 1/2 to the second power, it's 1/4. If you look at 1/2 to the third, it's 1/8. 1/2 to the fourth, it's 1/16. Your outputs, 1/2, 1/4, 1/8, 1/16, are getting closer to 0 as your power increases without bound. So you can take that formula that we had for finite geometric sequences, and as n approaches infinity, r sub n is going, r to the nth power, is going to 0. So if I take the first term times 1 over 1 minus r, then the sum of a geometric infinite series is equal to the first term over 1 minus r, provided your common ratio, its absolute value, is less than 1. So the sum of an infinite geometric series, if the absolute value of r is less than 1, then the infinite geometric series has the sum s equals the first term over 1 minus r. Again, if the absolute value of r is more than 1, the series does not have a finite sum. On example 7, we're going to find the sum of the infinite geometric series if possible, and if not, we'll need to explain why. So when I look at A, I have the summation from n equals 0 to infinity of 2 times negative 2/3 to the n. You need to recognize that this is a geometric sequence because 2 is my initial value, my first term, and here's the work to prove that by putting in 0 for n. The common ratio to the 0 power is 1, and therefore I get 2 as my first term. And then negative 2/3 is my common ratio. You have to remember that the sum of the infinite geometric series is the formula we just derived, which is the first term over 1 minus r. And here's the work for that. My first term is 2 over 1 minus my common ratio of negative 2/3. 1 minus a negative 2/3 is a positive 2/3. 1 plus 2/3 gives me 5/3. When I evaluate the complex fraction, I take 2 times the reciprocal, which is 3/5, and that gives me 6/5. So the sum of this infinite geometric series is 6/5. When we look to example B, notice how my common ratio is 4. The absolute value of 4 is not less than 1. So it does not have a finite sum, because in order for a geometric series, infinite geometric series, to have a finite sum, the common ratio must be less, the absolute value of the common ratio must be less than 1. 4 is greater than 1, therefore it does not have a finite sum. On C, all we did was give you actual physical terms of the sequence instead of giving it to you in summation notation. So if you notice, my first term is 9. We have to find the common ratio, and we have to ensure that that common ratio is, its absolute value is less than 1. So if I take 6 divided by 9, and then I take 4 divided by 6, and I was just being lazy in terms of the typing, but if you take 8/3 divided by 4, we do get the common ratio of 2/3. So I can go ahead and apply the formula for the sum of an infinite geometric series, which is the first term over 1 minus r, because 2/3 has an absolute value that is less than 1. My first term is 9. I take 1 and I subtract my common ratio of 2/3. So that's 9 over 1/3. And when I evaluate that complex fraction, 9 times the reciprocal of 3 over 1, the finite sum is 27. And here we are at example 8, nerd alert, I think this is a pretty cool problem. We're going to find the rational number representation of the repeating decimal. So a lot of you are familiar that 0.33333 repeating is 1/3, or 0.6666666 repeating is 2/3, or that 0.1111111 is 1/9. But what about 1.38 repeating? That's not a common repeating decimal, and I think this is a really cool way using a series to figure out what that repeating decimal is. So if you think about 1.38 repeating and we break it down into parts, it's 1.3 plus 0.08 repeating. Well, you can think of 0.08 repeating as a sum of all these decimals of 0.08, 0.008, plus 0.008, and so on. So you can define not the 1.3 part, but the repeating decimal part as a sum of an infinite geometric series. So from n equals 0 to infinity of 0.08, and you're just multiplying by 0.1 because you just keep moving the decimal place over to the right for each term. Well, if I apply the formula for the sum of an infinite geometric series, my first term is 0.08 over 1 minus the common ratio of 0.1. Now, I need to not have these in decimals if my goal is to make this a rational number. So I need my answer as a fraction. So I can think of 1.3 as 1 3/10. I can think of 8/100 as 8 over 100. And 1 minus 0.1 is 0.9 or 9/10. So I need to simplify my complex fraction. 8/100 reduced to 2/25. I'm going to multiply by the reciprocal of 9/10. Please, and the 1 and 3/10 I made as an improper fraction. 10 times 1 is 10, plus 3 is 13, and I get 13/10. Please excuse my dear Aunt Sally tells me to do my multiplication first, so 2/25 times 10/9 yields 4/45. And then when I take 13/10 plus 4/45, they have a common denominator of 90. 1/17/90 plus 8/90 gives me 1/25/90. So 1.38 repeating is equivalent to 25/18. And welcome to our last example, example 9, where this should be a flashback. I know, math, it's all related to exponential functions. So if we have the principal of $2,500 invested at 4% interest, we're going to find the amount after 20 years if the interest is compounded annually, semi-annually, quarterly, monthly, and daily. This should also ring a bell from personal finance. But what you might not think about is this is of the form of a geometric sequence. Your principal represents your first term. 1 plus r over n represents your common ratio. So this is just another application of something that you already know. So when I want to find the total amount in my account, if I compound annually, this implies that n is equal to 1. So I plug in 1 into the formula. reminding ourselves that 0.04 represents the decimal percentage of 4%, and I output $5,477.81. That's something I just typed in my calculator. For Part B semi-annually, that implies that n is 2. Again, I substitute in 2 for n, and I yield $5,520.10. Notice that there is an increase, and that should happen. The more we compound, then the more interest on top of interest we're earning. Part C, when we imply quarterly, we imply that n is equal to 4. So I input 4 into the formula, yielding $5,541.79. For Part D, monthly implies I'm compounding 12 times a year. So I yield $5,556.46. And finally, for E, daily would imply a 365. Yes, I know there's 366 in a leap year. We're going to stick with the 365. And I output $5,563.61. So hope this section makes sense. Hopefully you're seeing a lot of the parallels of geometric and arithmetic sequences, but you need to make sure that you keep your formulas straight and understand that on the test, they're going to be mixed up. So make sure that you maybe are going back and forth and practicing arithmetic and geometric type questions on the same day to prepare for your test. So your learning opportunity number 2 is page 582, 37 to 81 odds, 91, 95, and 97. Good luck.